Okay, so let's try this problem again. But this time, what we're going to do is do it completely with another concentration. So let's say we've got a concentration solution of 0.60 molar vitamin C. So again, I'm going to start with the same equation. So we got ascorbic acid plus water is in equilibrium with H3O plus and ascorbate ion. Okay, both of these are aqueous. All right, so initially we have a 0.60 molar concentration of ascorbic acid, no concentrations of ascorbate ion or hydronium ion. The change, we know that ascorbic acid has to go down and hydronium and ascorbate ion have to go up, so that at equilibrium, the concentration of ascorbic acid is going to be 0.60 minus X. Concentration of hydronium ion is plus X, and the concentration of ascorbate ion plus X as well. All right. So if we were to set up a Ka expression, the Ka would be the concentration of H3O plus, which is X, times the concentration of ascorbate ion, X, divided by the concentration of ascorbic acid, 0.60 minus X. And this is equal to the Ka, which is 8.0 times 10 to the minus fifth. All right, so let's do a little bit of cleanup. So X times X is going to be X squared. And if we apply the approximation here, okay, so we're gonna use that assumption. If we use that assumption here, that the concentration of X is not going to change from a whole lot, not going to change the 0.60 a whole lot. So we can say that the denominator is really just going to be 0.60. This is equal to 8.0 times 10 to the minus fifth. So if we solve for x squared would be equal to 8.0 times 10 to the minus fifth times 0.60. And then if we take the square root of both sides, square root would give us, let me show you the steps. I apologize. So x squared would be equal to 8.0 times 10 to the minus fifth times 0.60, which is 4.8 times 10 to the minus fifth. And if we take the square root of both sides, x would be equal to 6.9 times 10 to the minus third. So that means that the concentration of H3O plus would be that value, 6.9 times 10 to the minus third. And if we take the pH of that, which is equal to the negative log of the concentration of hydronium ion, the pH would be 2.16. All right, so think about what the problems that we've done in the last video and what we just did. We saw that when the concentration was 0.20 molar for vitamin C, the pH was about 2.40. And when the concentration of ascorbic acid was 0.40 molar, we saw that the pH was 2.25. Okay. And then we just saw in this problem that if the concentration of ascorbic acid was 0.60 molar, the pH went down to 2.16. So we're seeing that as the concentration of H3O plus increases, we see that the pH is really going down. Okay. Now, every time we double the concentration, it seemed that the pH was also going down, but we can't say that was a proportional amount. Okay. So the pH is going down, but it's not proportional. All right. So that being said, let's try another problem. All right. So find the pH, the concentration of H3O plus, and the concentration of hydroxide ion for a 0.150 molars aspirin solution. So aspirin is really coming from this compound, which is salicylic acid. Okay, which I'm going to shorthand as SA plus the H, because we know it's got to be an acid. Now, one thing that we got to look up before we do anything else, going back to our table of weak acids, is salicylic on this table, and it is not. I am not seeing that. So we've got to look up the value of salicylic acid. So salicylic acid, if I was to look up that, if we look it up in a different textbook or a different chart, that Ka is going to be 3.0 times 10 to the minus fourth. All right. So we need to we're going to set this problem up just like we did the other ones. So we've got our reaction, salicylic acid plus water is in equilibrium with H3O plus and salicylate. Okay. Everything is aqueous except for the water that's liquid. Okay. And initially, the concentration of aspirin is going to be 0.150 molar. Everything's at 0. The change, aspirin's got to go down. The others have to go up so that at equilibrium, the concentration of salicylic acid is 0.150 minus X. Concentration of hydronium ion is X. Salicylate is plus X. Okay. So what we're going to do, let's get our equilibrium expression. Ka is going to be equal to the concentration of H3O plus times the concentration of salicylate divided by the concentration of salicylic acid. Okay, or X for the concentration of H2O plus, X for the concentration of salicylate, and then 0.150 minus X for salicylic acid, and this is equal to 3.0 times 10 to the minus fourth. Okay, all right, so we've got our expression now. If we apply the assumption here that the change in X is going to be so small that it's not going to really change our initial concentration all that much, we're going to say that X squared, so X times X gives us X squared. The denominator is really 0.150. Okay, so X is not going to change the denominator all that much. This is equal to 3.0 times 10 to the minus fourth. Okay, so I want to get X by itself, so I'm going to multiply both sides by 0.150. So X squared is equal to 3.0 times 10 to the minus fourth times 0.150, or X squared is equal to 4.5 times 10 to the minus fifth. Now, if I take the square root of both sides, we get that X is equal to 6.7 times 10 to the minus third. So that's our X value. Now, one thing that we should do, we probably should do now before we get, really invested in this problem, too late. But let's double check to make sure that that this approximation worked. Okay. So what I'm going to do, let's take that part up here. So if we take the initial concentration, which is 0.150 molar, and that's my denominator, I'm going to put the X on top, so 6.7 times 10 to the minus third times 100%. What is the percent ionized? So it looks like it's going to be really close to about 4.5%. So it's still under 5, so our approximation holds, but we're getting real close to that area, like we probably should be using the quadratic formula. All right, but our approximation still works. We're good. All right, so now that we know that the concentration of H3O plus is equal to the concentration of salicylate ion, and that's going to be 6.7 times 10 to the minus third molar. We can also find the concentration of ascorbic acid, which is, it's going to be still pretty close to 0.150. It's going to be like 0.49 or 48. Okay. All right, so we need to find, according to this problem, we need to find the concentration of hydronium ion, which we did. We need to find the concentration of hydroxide ion, and we also need to find the pH. So we know the pH is equal to the negative log of the concentration of hydronium ion, or 6.7 times 10 to the minus third. And so the pH of this solution is going to be about 2.17. All right. Now we also need to find the concentration of hydroxide ion, and to find that we got to use the Kw. So remember that Kw is equal to the concentration of hydronium ion times the concentration of hydroxide ion. And so the concentration of hydroxide ion, if we rearrange this will be Kw divided by concentration of hydronium ion. Okay? Or 1.0 times 10 to the minus 14th divided by the concentration of hydronium ion, which was 6.7 times 10 to the minus third. Okay. All right. So concentration of hydroxide ion, if we do that work, concentration of hydroxide ion should be about 1.5 times 10 to the minus 12th molar. All right. So that's pretty much how we do this problem. All right. All right. So I know we talked about percent ionization already, but just to be clear, what is the equation to calculate percent ionization? So the amount dissociated is going to be equal to the concentration of acid that was dissociated divided by the initial concentration of the acid times 100%. Now, is percent ionization proportional or to the concentration? Well, it's going to give you another logarithmic curve. So, if you, let's say, you start with 4.2% dissociated, excuse me, as you increase the concentration, the percent dissociation is going to increase by a factor of 10 when the concentration decreases by a factor of 100. Okay. All right. So one more topic before we talk about weak bases, and that is polyprotic acids. Now, some classes could potentially spend a lot more time on polyprotic acids. Because time is pretty short for the summer, I'm gonna keep things pretty straightforward. Okay, so I'm gonna give you the quick and dirty version of polyprotics. So as we've seen, as we've dealt with right now, all we've dealt with is monoprotic acids where there's one proton. But if you get into sulfuric or phosphoric or carbonic acid, you got more than one proton. Okay, so let's take a look at sulfurous acid, H2SO3. Okay, if H2SO3 reacts with water, it's going to form an equilibrium between H3O plus and HSO4 minus. Okay, now this HSO4 minus, however, can also react with another water molecule, and you can get H3O plus and the sulfate ion, 2 minus. Okay, so an acid, a diprotic acid, can go through two of these acid-base reactions. Okay, where I just realized that I just wrote H2SO4 minus. It's HSO4 minus. So this HSO4 minus, keep in mind that this species right here, it's going to be amphoteric because it can give us, it can act as an acid or a base depending on which reaction we're looking at. All right, so those are your two reactions. You've also got the water reaction, the autoionization reaction with water. So water reacts with water and forms H3O plus and OH minus. All right, so let's take a look at the Kas for this reaction. So the Ka for the first reaction is going to be 1.5 times 10 to the minus second. The second reaction is 6.3 times 10 to the minus eighth. And then the Kw is going to be 1.0 times 10 to the minus 14th. Okay, so what can we conclude about these reactions? Okay, so what can we conclude about the relative importance of each reaction if sulfurous acid is added to pure water? Well, here's what we can tell. Because the first Ka is 10 to the minus second, compared to 10 to the minus 8th for the second reaction. The first reaction is very important because that's where the concentration of hydronium ion is really going to be coming from. Okay. Yes, the second reaction is going to provide a little bit. Yes, the third reaction also provides hydronium ion a little bit, but not as much as this first reaction will. And again, we know that because the Ka is so much bigger than the other two. Okay. So the first reaction is very important for the concentration of H3O+. Okay. The second reaction is not so important. It happens, and it's good to know that, but from the viewpoint of the H3O+, it's not really, it's really not producing a whole lot of hydronium ion as compared to the first reaction. Now, what about that third reaction? The third reaction is important if we're looking for hydroxide ion. Okay, so then that third reaction does become important. All right, so what can we conclude about adding sulfurous acid to a very basic reaction? Well, what we know is that hydroxide ion reacts with water, or it reacts with hydronium ion. Reacts with hydronium ion, H3O+. Okay. And when that happens, it pulls the first reaction towards products. Okay, and it reduces H2SO3. And then the third reaction will go towards product formation. Because essentially, the third reaction would be a titration. If the first reaction is producing H3O+, okay, if that reaction is producing H3O+, then that H3O+ is really going to be titrated against that hydroxide ion. Okay, and so what can you conclude about adding sulfurous acid to a very acidic solution? Well, we know that H3O+ will react with hydroxide ion, with OH minus, in reaction 3, and it actually pushes all three reactions to the left to favor reactants. Okay. Now, you could do the same kinds of problems that we were doing previously, finding the concentrations of species at equilibrium. That right now, for all intents and purposes, for the what you're going to do for this class, that's beyond the scope of what we got to do. If you go on further to analytical chemistry, you would be getting into those kinds of concentrations. But between the last video and this video, we now know how to calculate the concentrations of species of a weak acid reacting with water.